VLLM prove the audience wants local serving, but if you care about throughput under real load, SGLang is the more interesting next stack to benchmark and tune. This is the setup you'll be able to run after this, which serves a local model, handles concurrent prompts, and reports throughput and latency to guide tuning. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Serving a local model is about more than running a binary. The hard part is keeping the model responsive when many requests hit at once. SGLang in Python. Serve LLMs locally with better throughput is a small systems approach to that problem. It helps you measure real throughput, observe latency tails, and make targeted changes so your local server feels fast under load. People choose this when they need predictable latency on a single machine or a small cluster, and when cloud latency or cost is unacceptable. At a high level, we want three things. 1. Verify the server is reachable and gives correct answers. 2. Measure first byte latency to reduce perceived wait. 3. Measure throughput and tail latency under concurrency, so we can tune parameters. Success looks like sub-second first token latency for tiny completions, predictable scaling of throughput with workers, and P95 numbers you can reduce with simple knobs. Conceptually, think of SGLang as the glue between your Python code and a model running locally. It offers an OpenAI-compatible surface, so existing clients work. The goal is not more model quality. The goal is consistent performance and clear measures. Strengths include local control and low cost at scale. Weaknesses are the need to monitor and tune. You trade managed convenience for observability and performance wins. We will build a tiny test harness. It pings a local SGLang server, streams a response to see first token latency, runs a small concurrent batch to compute queries per second, compares short and long responses to measure token cost, and then collects a P95 under concurrent load. You do not need to run a full deployment to follow this in Python. The code snippets are minimal, deterministic, and focused on timing. Now we start with a quick readiness check. This snippet verifies a local SGLang server by issuing a tiny chat completion and timing the round trip. The OpenAI client is pointed at SGLang's OpenAI-compatible base URL, and the model name is stored in the variable model. A quick request is sent with temperature set to 0 for determinism and a small max tokens to keep latency low. The variable DTMS measures elapsed time in milliseconds, and LC captures the number of characters returned. These two values provide an immediate readiness check without overwhelming the server. The printed numbers confirm the server is reachable and give a first latency reading with minimal output size. Next, we will stream a response to capture how quickly the server delivers the first byte. This example streams a response from SGLang to capture time-to-first-byte and reduce perceived latency. It starts a timer in T0, then calls chat.completions.create with stream true, so partial chunks arrive incrementally. Each chunk exposes delta content through chunk.choices0 delta.content. The code records the timestamp when the first non-empty delta is seen. All deltas are appended into the text list to reconstruct the full message and count words. Temperature is 0, and max tokens is small to keep behavior consistent and quick. If you increase max tokens, total completion time grows, but the first token can still arrive quickly. The printed values show first token latency and concise output size. Now we'll stress the server with a small concurrent batch to observe throughput. This snippet runs a short parallel batch against SGLang to observe throughput under concurrency. A small list of prompts is created. Then a ThreadPoolExecutor with 4 workers issues requests simultaneously using chat.completions.create. The Lambda builds each request with a deterministic temperature and a modest max tokens, so variance stays low. The elapsed time dt is measured around the entire batch, and QPS is computed by dividing the number of requests by the total time. Increasing max workers can raise QPS until the server saturates. Too high, and queuing can slow overall progress. The printed throughput quantifies how well your local server handles a small concurrent burst. Next, we will compare short and long responses to see how tokens affect latency. This snippet measures how response length affects latency on SGLang by changing max tokens. The helper function ask sends a deterministic request with chat.completions.create, timing the call and returning milliseconds. It runs twice with different caps, first at 32 tokens and then at 256. So the only meaningful change is the allowed length of the completion. The variable D1 captures the short response latency, while D2 reflects the longer response. Their difference highlights the incremental cost. Increasing max tokens typically raises latency roughly in proportion to generated tokens, while decreasing it lowers latency at the cost of brevity. The printed numbers reveal the trade-off between speed and completeness. Finally, we will gather a P95 under concurrent load to capture tail behavior. This example exercises a small concurrent load on SGLang with a lightweight safety guardrail. A concise system message sets behavior expectations, and a short list of user prompts drives work. The function 1 records each request's latency while calling chat.completions.create with fixed temperature and a modest token cap. A ThreadPoolExecutor issues several requests in parallel, and the collected latencies are sorted to compute a P95 estimate that reflects tail performance. Raising max workers or max tokens will generally increase P95. Lowering them reduces tail latency, but also reduces throughput or output length. The printed P95 helps validate a baseline before tuning further. You can map this toy harness to a real project by replacing the example prompts with your own workload, and by routing metrics to your existing telemetry. The same measurements guide whether to add more workers, cap tokens, or optimize batching. Keep the tests deterministic, so changes reflect tuning, not data noise. Recap in 3 quick points. What it is: a simple Python-driven test harness for SGLang that measures readiness, first byte latency, throughput, token cost, and P95 tail. When to use it: when you run a model locally and need predictable latency under real traffic. One caveat: local performance depends on hardware and model size, so numbers vary and tuning is required. Next step: tune the number of workers under your typical prompt mix and measure the effect on QPS and P95. That single knob often yields the biggest practical win before changing model size or hardware. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.